Welcome back to Geometry. We are at Unit 3. We're going to start off with the mid-segment theorem and then work our way into 5.2 bisectors and triangles. So for the mid-segment theorem, there's a few things that we should review. One, it's saying that the mid-segment of a triangle is half the length and is parallel to the third side. Now, let's underline this third side, make sure we understand what it means. So when I think of a triangle, we have one side, two sides, and a third side. So we can see these arrows right here, which means these two lines are both parallel. And so that's what it means, is that the mid-segment, which is this line right here, is going to be parallel to the third side, which is this side right here. Okay, so these two sides have to be parallel. That's the first condition. The second thing that needs to happen is that this segment that is parallel to the third side is going to bisect sides 1 and 2 in half. So we see that with 34 and 34. Now clearly this shape's not drawn to scale because this 34 looks longer than this 34, but you get the idea. These two sides are the same and these two sides are the same. So when we have these conditions, that means this segment has to be a mid-segment. Alright, well, we have a formula to find out our mid-segment, and our mid-segment is going to be equal to 1/2 and then multiply that by our third side. So in looking at this problem, we're already given 20 as the mid-segment. So we're going to substitute 20 in for the mid-segment. It's going to equal 1/2, and the third side we will substitute in x. Solving for x, times 2 on each side, times 2 on each side, we get 40 is equal to x. And really, we didn't need to do all of this work, but I'm just showing you all of my work. You could have just looked and saw, hey, since our mid-segment's 20, that means our third side has to be 40, and you can move on. Next shape, again, we would like to see that we have arrows here, that these two lines, or that these two segments are each parallel. I see one mark and one mark, which is great, and 2 marks and 2 marks. So that means that this segment is in fact a mid-segment. It has to be. It fits the rules. So we're going to take our mid-segment. It's going to equal the half of our third side. And so in this problem, our mid-segment, let's substitute 2x minus 5 equals 1/2, and then our third side is 18. 2x minus 5 is equal to 9. 2x equals 14. X equals 7. Last thing that we might want to do is we can plug in 7. We get 14, and 14 minus 5 would be 9. Alright, moving down below, we have a new theorem. It's called our perpendicular bisector theorem. It says every point on the perpendicular bisector of a segment is equidistant to the endpoints of that segment. So let's make a drawing, because this is a great definition. However, without a drawing, we're not really sure what's being said. So let's put endpoints on segment AB. And so it's possible that we can measure segment AB because it has endpoints. We cannot measure line CD because it's going to go on forever. But we're given it in this problem that line CD is the perpendicular bisector of segment AB. Since we're given that, we can now make markings, and we can now mark these two sides are the same. D, this D should have been put right here, so I'm going to move D because D stands for this point here. Alright, so we know that these two segments are both congruent because line CD is a perpendicular bisector. We can also put 90-degree angles here and here. So that's what I can mark. So on our proof, let's draw an arrow down to here. This is going to be given. We can then say that excuse me, bless me, sorry about that. We can then say that segment AD is congruent and equal to segment BD. And why, you might ask? Well, that's going to be definition of perpendicular bisector. Okay, which says that since CD is a perpendicular bisector, that means segment AB will get cut in half, and that's why we're allowed to say AD is congruent equal to BD by definition of perpendicular bisector. Alright, we're also allowed, let's label this angle 1 and angle 2. We can say angle 1 is congruent equal to angle 2. And why is that? Well, we can say that all right angles are congruent. Alright, so we don't really have a plan yet as to how we're going to prove that AC is congruent equal to CB. So let's think about this. We're told on this theorem that every point on the perpendicular bisector of a segment is equidistant to the endpoints of that segment. So let's take a look at what that means. Go ahead and put a point on C. And so we're going to say that every point in this problem to the right, this is referring to point C. So really we can read this as point C on the perpendicular bisector is equidistant to the endpoints of that segment. What does this term mean? Equidistant. Well, it means that if you drew a line or a segment from CA and a segment to CB, that means these two lengths would each be the same length. They're each congruent. That's what it means that this point C is equidistant to point A and point B, or the endpoints of this segment. Now, I can do that a few more times. Let's say I moved point C down here, okay, and I could draw these two lines, okay, and these two lines would also each be the same. They're congruent. And I could do it a third time. I could move point C to here and then draw this and say that these two segments are each congruent. Okay, so there's many ways that I can show that. Alright, so our proof, let's go ahead and erase all of this so that we can see it better. We're going to erase this. Whoops. Good, and then let's fill this back in. No, we don't want to do that. Let's get our pen back. There we go. And okay, here we go. So here's our shape. We have a 90-degree angle. We have these two sides are each congruent. Okay, we are trying to prove that AC is congruent equal to CB, so I'm going to have to use the eraser again. And let's erase these two marks and these two marks. Alright, and hopefully now this makes more sense. So looking at our drawing, we have side angle and side angle. So my plan here is I'm going to use CP/CTC first. I guess I will do that second. First, I have to prove that the two triangles are congruent. That's going to be my plan, because if I can prove that these two triangles are each congruent, that means AC has to be congruent equal to CB by CP/CTC. And I can do that rather easily, because statement 4, we can say that CD is congruent equal to CD, and that's by the reflexive property. So let's put 2 marks here. And so now I can say that these two triangles are congruent. So triangle CAD is congruent equal to triangle CBD. And why is that? Well, it's going to be side angle side. And then last but not least, statement 6, I can now say that segment AC is congruent equal to segment CB, which is what we were trying to prove. Let's draw down our arrow. And that's going to be because of CP/CTC. Okay, in Algebra 3-4, you're going to learn about the conjugate. Okay, for right now, just know that in a sense this is going to create a difference of squares, and I'll show you what I mean by that. But that would be like if we had x minus 4 times x plus 4. This would be considered a difference of squares. And what would happen here is the middle term when I FOIL is going to equal 0, so I just get x squared minus 16. Now recall that if we had a problem, let's change the ink color. If we had a problem like, if we change problem 1 to 7 over rad 3, well, we would multiply by rad 3 over rad 3. We would get 7 rad 3 over rad 9, which is 7 rad 3 over 3. And the reason why we do that is we're not allowed to have a square root on bottom. Okay, but if I just multiply this problem by rad 3 over rad 3, I would end up getting 7 rad 3 over rad 6 minus 3. And we still have a, or sorry, not rad 6. I would get 2 rad 3 minus 3. And we still have rad 3 on the bottom. And these won't cross out because we have subtraction here. So we can't do this. It won't work. We'll still have a square root on bottom. So what I'm forced to do is multiply by the conjugate. And that's going to be 2 plus rad 3. And the reason why it's 2 plus rad 3 is this creates a difference of squares. And so we multiply this on top and on bottom. So on top, I'm going to get 7 times 2 is 14. 7 times rad 3 is 7 rad 3. And on bottom, when I FOIL, I'm going to get 4 plus 2 rad 3, right? And then underneath, minus 2 rad 3, and then minus rad 9. And when we simplify, 14 plus 7 rad 3 over, and this would be 4, and then 2 rad 3 minus 2 rad 3 is 0. That gives me minus 3, so 14 plus 7 rad 3 over 1, which anything over 1 is just itself, so 14 plus 7 rad 3 is my answer. Alright, let's do the same for the next problem. We're going to multiply by its conjugate, which will create a difference of squares, so rad 6 minus 1, rad 6 minus 1. We get rad 30 minus rad 5 over, that would give me rad 36, and then that would be minus 1, middle terms cross out. We end up getting rad 30 minus rad 5 over 6 minus 1 is 5, and here is my answer. Now, I hear you. At first you're saying, wait a minute, rad 30 minus rad 5 is rad 25. No, it's not. These aren't like terms. We can't add or subtract. Rad 30, when we break down rad 30, we have 10 times 3, 3 is prime, 2 and 5. We don't have any pairs, so we can't pull anything out. So rad 30 is reduced. We can't reduce it any farther. Alright, next we're going to multiply by its conjugate, 4 minus rad 7, 4 minus rad 7. Alright, we're going to get 9 rad 2 times 4, that's 36 rad 2, minus 9 rad 14, over 16 minus 7. So next I have 36 rad 2 minus 9 rad 14 over 9. From here we should definitely use the V trick. We have to divide 9 into 36 and 9, so the V trick looks like this. 36 over 9 is 4. We get 4 rad 2, and this becomes 1 and 1 minus rad 14. These aren't like terms. That's my answer. Alright, then we also have what's called the converse of the perpendicular bisector theorem. And it's down below. We're going to make a drawing of this on the next slide, so I'll join you on the other slide. Okay, so again, we are dealing with the converse of the perpendicular bisector. Okay, so we're going to say if point D is equidistant to points A and C, or if, sorry, we are just saying that point D is equidistant to points A and C. That's why we have these two marks. Okay, so if we're shown a drawing that looks like this, okay, then since we know that these two sides are the same, BD must be the perpendicular bisector of segment AC. Okay, so all we need to be shown is that these two sides are the same, and if we're shown that, then we get to do this, and we get to make this marking. All right, and then if we keep going, we can then say that these two triangles are each congruent. So triangle bad is congruent equal to triangle BCD. And how do we know that? Well, this is going to be by, we have side-side angle and side-side angle. Remember, we can't use SSA, that won't work, but the form of the SSA that works in right triangles is called the HL theorem. So these two triangles are congruent by the HL theorem. Alright, so problems that will show up on quizzes and tests look like the two below. You're being asked to find everything, so I would start with this shape on top. You're told that you have a box here and a box here, and these two sides are the same. Therefore, these two segments have to be the same. So we just say CA has to be 5. It also works down below. Okay, I can move this box here, this here. These two sides are the same, which means these two sides have to be the same as well, which also means that CD is a perpendicular bisector of segment AB. BD would have to be 6. Over to the right, if AB is 3x minus 1 and BD is 5x minus 11, first we have to prove that these two sides are the same. Alright, we're told in the problem that AC is congruent equal to CD. Without this piece, we would not be able to solve this problem. And since we're given that, we can put a mark here and a mark here. And we also know that by reflexive, that this segment is equal to itself. So these two triangles are congruent. Also, we would know that these two sides have to be the same because BC is a perpendicular bisector of AD. So 3x minus 1 equals 5x minus 11. 2x equals 10, x equals 5. And if we plugged 5 in, we would get 14 and 14. Alright, the last two theorems. We have every point, or the first theorem is called our angle bisector theorem. Every point on the angle bisector of an angle is equidistant to the side of the angle. So we definitely should make a drawing for this. Alright, let's draw an angle. And we're going to draw a ray that's going to bisect this angle. Here comes the ray. So these two angles are the same. Alright, and then we would also be shown that we could say that we have a point up here and we draw this segment and we call this length x, and we draw this segment and we call it y. And since these two angles are the same, I can then say that x has to be equal to y as a result. And so this is based from our angle bisector theorem. The other thing that I can say is that if you were told that x was equal to y, and let's say we didn't know that these two angles were each congruent. Let's just say that you had a ray, and you're told that x is equal to y, so let's put one mark here and one mark here. If you were shown these markings, then you can do the converse of the angle bisector and say if x is equal to y, then the ray is an angle bisector. Or even better, you could say that the angle 1 is congruent equal to angle 2 if we were to label this angle 1 and angle 2. Alright, if x is equal to y, then angle 1 is equal to angle 2 because the ray is an angle bisector. Okay, the last problems we have involve algebra review. We have a times b times b times b minus 2 times a times b. And I like to circle what they both share. We have an a, a b, an A, and a B. So these are my factors. So I pull out 1A, I can pull out 1B. Inside I'm going to have A times B squared, because I have A and then times B, and then minus 2. And so that's what the first problem factors to. Here we have 3 times x times x times x, y times y times y times y times y, and then minus 3 times x times x times x, and then y times y times y. So again, let's circle what we share in common. We have a pair of 3's. We have 3 x's here, so I can circle 3 x's here. That's what they share in common, our greatest common factor, so 3. And then we have 3 y's, and we have 3 y's. And so I'm going to pull out 3 y's, and then inside I'm going to write what we have left. We have 2 y's, we have 1 3, and an x. Alright, then on problem 4, these only share a y. We have a y, so we're just going to pull out 1 y. 2x, 3, y, I believe that's a 3, or it might be a 5, so I'll put y to the 4th, minus 8x, 4, y, 2, and then plus 3z, and that would be our answer. Thanks for joining us. See you next time.